welcome back everybody. So this section is called Systems of First Order, Linear, Homogeneous, Constant, Coefficient, Ordinary, Differential Equations. And I do apologize about how long that title is, but we've got 1, 2, 3, 4, kind of 5, and kind of 6 adjectives to equations, and even systems is kind of an adjective. The reason for so many adjectives is that differential equations are hard. It's definitely a hard subject. I mean, there are entire semester courses devoted to just ordinary differential equations. There's an undergraduate and graduate version of those two courses. Same goes for partial differential equations, undergraduate and graduate. And even that probably tackles 0.5% of what's out there. It's an incredibly hard topic to study. And it's primarily the topic that I study, so lucky me. But anyway, every adjective is a restriction, right? It's a restriction on a type, so it forces you into a smaller category. And in this case, after we put this many restrictions onto our differential equations, we get to a category that you all know how to solve. So after this many restrictions, you know what you need to solve them. And in fact, Schrodinger's equation, in a few of kind of the classic cases, falls into this category. So let's actually describe what we're talking about. Here we go. Definition: system of first order, linear, constant, coefficient, ordinary, differential equation. By definition, it is a system, big surprise, of equations where it's going, we'll write it in vector notation. So we've got a vector x, which depends on time, and we're going to take a derivative of it, right? So if you've forgotten the prime or apostrophe, means time derivative. Unless you're in physics, sometimes they'll use a dot instead of an apostrophe for time derivative. And we'll say that this vector is equal to a matrix M multiplying itself. And so this is a vector which depends on time. And of course, I've taken a time derivative of it, but it's equal to a matrix on itself. And there's this matrix here, which doesn't depend on time. And then every first order differential equation that you encounter, I mean, if you took a differential equations course, you would find this out for sure, but every first order differential equation has an initial condition. So you can usually write this as x of t0 equals another vector that you just call x sub 0. So there's an initial condition or an initial time. And you can think about really this x sub 0 as some initial place. So you've got initial time, initial place, and then think about x prime, that's really your velocity. Your velocity depends on an operation on where you are currently. So this is what a system of first order linear constant coefficient ordinary differential equations looks like. And we're going to analyze how to solve these today. So the solution is not even that hard. The solution is given by x vector of time equals e to the t minus the initial time of the matrix. So there's my matrix exponential showing up. And then this is a matrix multiplication on the vector, which is your initial vector. And so here's the initial time, the initial place, and the matrix exponential. And then your solution, of course, is just the object, the vector which evolves over time that results from all of that. That really is the topic for today, but we'll go ahead and analyze it in a few situations because we'll see that a lot of times people like to present differential equations and they don't necessarily hand them to us in this beautiful form that we would like to immediately solve with a matrix exponential. So sometimes, and really often, we'll be given something like, it'll look like a different system. It'll say something like x1 prime equals 3x1 plus 4x2, and then x2 prime equals 4x1 plus 3x2. It'll say something like x1 at time 0 is -1, and x2 at time 0 is 2. Solve for x1 and x2. And so it doesn't exactly look too terribly different than the above, but it also doesn't look exactly the same. So in some ways, it's useful to translate the later system to the earlier system. So we go ahead and translate this into a matrix vector. And I use this term ODE. This stands for ordinary differential equation. And we go ahead and translate. I think everybody can imagine where the matrix comes from. We certainly see a collection of 4 coefficients here. But let's start with the vector. So the vector we really want to imagine are kind of these x1s and x2s. That's like my vector x. So we'll say that x as a vector. And on the left-hand side, it has a prime. And we have to make an assumption here. There's really an assumption that everything is a function of t, even though it's not written. This is extremely common in differential equations to drop the independent variable, but I'm going to add it back in when I'm translating. And the first thing I'm going to do is define this vector x to have the entries x1 and x2 in it, or the vector as dependent on time would be like the entries x1 dependent on time, x2 dependent on time. So we make that choice first, and so the left-hand side becomes the vector prime, the first derivative of the vector, and what we get on the right-hand side is the matrix 3, 4, 4, 3, that's coming from the coefficients. And then that multiplies, and it doesn't look like this should be the case, but it multiplies x1, x2, right? Because if I go ahead and perform the matrix multiplication, the x1's ending up there, the x2 is ending up there, so that's my first line. And then same with the second line, the x1 ends up there, and the x2 ends up there. So this really is being multiplied by x1, x2, or in other words, since I'm using the vector notation on x, it really is that matrix multiplying the vector x, which is a function of time. And then we can do a very similar thing with our initial conditions. x1 and x2 translate over into x vector at what specific time? What is our initial time? 0. And that's equal to the initial vector on the right-hand side, -1, 2. And so now that it's written in this form, our life gets quite a bit easier, and we can actually go ahead and grab this solution formula. Grabbing the solution formula, we just identify the initial time as 0, so that t sub 0 is 0. Our initial vector is the vector -1, 2, and then our matrix just goes in the matrix exponential. So the solution is given by the formula x as a function of time, vector valued function of time, is e to the t minus the initial time, and in this case the initial time is 0, of the matrix 3, 4, 4, 3, and then you compute that matrix exponential and you act it on the initial vector, which was -1, 2. So we need to go ahead and compute this. And then also compute the multiplication on the vector if we're actually going to find our solution. So let's go ahead and compute that matrix exponential. E to the t, well, t minus 0 is just t. 3, 4, 4, 3. I need to diagonalize. This is going to be x to the e, x times e to the td. x inverse, and I have to actually go ahead and find what all of those terms are. So we'll diagonalize 3, 4, 4, 3 by finding eigenvalues. So go ahead and find eigenvalues. The determinant of 3 minus lambda 4, 4, 3 minus lambda is going to be 3 minus lambda squared. Minus 4 squared is 16. We get 9 minus 6 lambda plus lambda squared minus 16. 9 minus 16 is negative 7. So we get lambda squared minus 6 lambda minus 7 equals 0. Our quadratic formula goes pretty quick. We have lambda is negative b plus or minus the square root of b squared minus 4ac. That goes pretty quick. Two negative signs. I have plus 28 here. All over 2a. We get 6 plus or minus the square root of 64 all over 2, or 6 plus or minus 8, right? So 6 plus 8 is 14 over 2. 6 minus 8 is negative 2 over 2. 7 and negative 1. I've used this matrix before in some of my examples. It's one of my more favorite matrices to diagonalize. I think it's just so natural to get those eigenvalues. You get a good exercise going through everything. So we've got some eigenvalues. Let's find eigenvectors. First one, when lambda is 7, we're looking for 3 minus 7 is negative 4, 4, 4, and 3 minus 7 is negative 4. On x1, x2 equals 0, 0. If I write out horizontally, I have negative 4 x1 plus 4 x2. And keep in mind, the second row is always degenerate when it comes to eigenvalues or eigenvectors, and so I can just go ahead and solve this, and we immediately see that x1 equals x2 is our relationship. So our eigenvector corresponding to the eigenvalue 7 is x1, x2, but because they're the same, this is x1, x1, or rather, our eigenvector corresponding to 7 is the vector 1, 1 associated to lambda equals 7. We do the same thing when lambda is equal to negative 1. 3 minus negative 1 is 4. 4, 4, and 3 minus negative 1 is 4. Against x1, x2 gives me 0, 0. I can read horizontally and find out that 4x1 plus 4x2 is 0, or rather that x1 is negative x2. That's my relationship, so I recover that x sub negative 1 is x1, x2, or in terms of just x1, I have x1 negative x2, x1 negative x1, or rather letting them be 1, I have 1 negative 1 associated to lambda equals negative 1. Those are my two eigenvectors, and now I can finish my diagonalization. Up top, since I found my eigenvectors, they were 1, 1, 1, negative 1. Against e to the t diagonals, where my eigenvalues go in the diagonal, 7 and negative 1 are my eigenvalues. Then I need to invert this first matrix. It's going to be 1 divided by negative 1 minus 1, also known as 1 divided by negative 2. I then swap a and d and make b and c negative, and I can go ahead and distribute the negative sign and make this look a little bit prettier as the following. You can see why this is such a nice matrix to diagonalize in a lot of these examples. So there's the diagonalization, and in fact I can compute one step farther because I know how the exponential and the diagonal works. We get e to the t times 7, or 7t, 0, 0, e to the minus t, and then a 1/2, 1, 1, 1, negative 1. So I'm going to grab this and pull it down so we can write it out a little bit more still. Our matrix exponential e to the t 3, 4, 4, 3 was 1, 1, 1, negative 1, e to the 7t, 0, 0, e to the minus t, 1/2, 1, 1, 1, negative 1. We need to go ahead and perform the multiplication. The first multiplication gives me, looking at rows against columns, it gives me e to the 7t, e to the negative t, e to the 7t, and negative e to the negative t, against 1/2, 1, 1, 1, negative 1. And we'll do one more multiplication here, and that's going to be rows against columns, giving me 1/2. Then I have e to the 7t plus e to the minus t, and then top right gives me e to the 7t minus e to the negative t. Bottom left gives me e to the 7t minus e to the negative t. Bottom right gives me e to the 7t plus e to the negative t. And if I want, I can distribute the 1/2 e to the 7t plus e to the minus t over 2, e to the 7t minus e to the minus t over 2, e to the 7t minus e to the minus t over 2, and e to the 7t plus e to the minus t over 2. That's my matrix exponential. Let's go back to the true solution here. The solution is the matrix exponential acted on the initial condition. So the initial condition there is -1, 2. So I get to my answer here. And I have to multiply this by -1, 2. Multiply by initial vector, -1, 2. That's going to give me e to the 7t plus e to the t over 2, e to the 7t minus e to the -t over 2, e to the 7t minus e to the -t over 2, and finally e to the 7t plus e to the -t over 2. Against the initial vector, -1, 2, we're performing one more matrix vector calculation, all rows against all columns. That's going to give me an output of -1 copies of the first case, so I have negative e to the 7t minus e to the -t over 2. That's -1 copies of the first, and then 2 copies of the second. I'm going to add e to the 7t. I'm going to subtract e to the -t because I've multiplied that term by 2. Same in the bottom row. I have negative copies of the first, so negative e to the 7t plus e to the -t all over 2, plus 2 copies of the second. The 2's cancel. I have e to the 7t plus e to the -t. I can go ahead and simplify. Looks like I have a positive one copy of e to the 7t and a -1/2 copies of that. So I have an overall 1/2 copies of e to the 7t, and I have -1/2 copy e to the minus t and another negative. So I have 3/2 copies of e to the minus t. I have -1/2 copies e to the 7t and a positive 1 copies e to the 7t, so positive 1/2 e to the 7t. And then in my last term, I have 2 copies of positive e to the t, negative t with a 1/2 and a 1, so I have a total of 3/2 of those e to the -t. So this is my solution as a vector. So that's the vector x of t. My solution to the original ODE, let's recall what the original ODE was presented as. It was x1 prime is 3x1 plus 4x2. x2 prime is 4x1 plus 3x2. Then we had that x1 at time 0 was equal to -1, and x2 at time 0 was equal to 2. Written like this, I just wanted an x1 and an x2, and all I need to do to extract those is read off the rows as x1 and x2. So reading off the top row, we find x1 was 1/2 e to the 7t minus 3/2 e to the -t. And the second row is 1/2 e to the 7t plus 3/2 e to the -t. This is the true solution to the original ODE I asked. So let's go ahead. We've already done this one example of this one. Let's go ahead and verify it's a solution. So what does it mean to verify a solution to an ODE? So verifying the solution is simply to compute all terms and check that equalities are actually valid. So there's really a total of 1, 2, 3, 4 equalities in the ODE, so I have to go ahead and ensure that all 4 of those are valid. What that's going to look like here is, let's just check the first one. So let's check if x1 prime equals 3 copies of x1 plus 4 copies of x2. We can do this by taking a derivative of x1. So prime, keep in mind, is just a time derivative. So we go ahead and compute a time derivative of that, and we end up with, well, a derivative in time of e to the 7t is just 7 e to the 7t, so I have 7/2 instead of 1/2 e to the 7t. And then subtract e to the minus t, a derivative of e to the minus t will be negative e to the minus t, so the minus becomes a plus, 3/2 e to the minus t. So that's me computing x1 prime, that's computing this term. I should go ahead and compute the other side. So let's compute 3x1 plus 4x2. Well, 3 copies of x1 is 1/2 e to the 7t, minus 3/2 e to the negative t. That's 3 copies of x1. I can compute 4 copies of x2. What is x2? It's this. So 4 copies of 1/2 e to the 7t plus 3/2 e to the negative t. And now I should go ahead and simplify. Let's simplify. Going ahead and simplifying, I have 3/2 e to the 7t minus 9/2 e to the minus t plus 4/2 is just 2 e to the 7t plus 12/2 is just 6 e to the negative t. And then we need to go a little bit farther and simplify yet again. All terms of 7t, I've got 3/2 plus 2 is a total of 7/2 e to the 7t. And negative 9/2 plus 6 is 12/2, so I have a total of 3/2 of e to the minus t. At this stage, we just check, are these two the same? And we look and we say, look at that, they are the same. So we verified the very first of 4 equalities. We're going to verify the solution. The second equality, we're going to check if x2 prime is equal to 4x1 plus 3x2. Well, to do that, we need to check or compute x2 prime. As before, the prime is just a time derivative. And if I scroll up to wherever x2 is, there's x2, and take a time derivative of x2, that's going to give me 7/2 e to the 7t, and it's going to give me a negative 3/2 because of the negative sign coming from the chain rule on e to the minus t. We also can go ahead and compute 4 copies of x1 plus 3 copies of x2. It's going to be 4 copies. Well, x1, it's not on the screen right now, but there it is also on the screen. So we're going to do 4 copies of 1/2 e to the 7t minus 3/2 e to the negative t. We're going to add 3 copies of x2, which is 1/2 e to the 7t plus 3/2 e to the negative t. And we'll go ahead and simplify these. And when we do, what we get is 4 times 1/2, so we get 2 copies of e to the 7t. 4 times negative 3/2 is negative 6 copies of e to the minus t. We're going to have 3 copies of 1/2, or 3/2 e to the 7t. We're going to have 9/2 e to the negative t. Combining all terms of e to the 7t, I've got 2 plus 3/2, that's a total of 7/2 e to the 7t. And I've got negative 6 plus 9/2, negative 6 is negative 12/2. 12 minus 9, we have negative 3/2 e to the negative t. As before, we're looking here, and we're comparing them to one another. Once again, those are the same, so we can verify this equality. We have 2 more equalities from the original. So we verified this, but we've got 2 more. Those are just the initial condition equalities. So all we need to do is plug in t equals 0. Plug in t equals 0. So now we go back to x1. We're going to check if x1 at 0 equals negative 1. Let's see, x1 at 0 is, well, x1 is on the screen, it's right there, so we're going to grab that, which is 1/2 e to the 7t minus 3/2 e to the negative t. That gets evaluated at t equals 0. So I'm just going and I'm grabbing the 0 and plugging it in for both places in t. That's going to give me 1/2 times e to the 0 minus 3/2 e to the minus 0, but both e to the 0 and e to the minus 0 are equal to 1, because minus 0 is 0. Any number to the 0 power is 1. This is just 1/2 minus 3/2, and so we have a total of negative 2/2, also known as negative 1. And we're also going to want to check to see if x2 at 0 is equal to 2. And to do that, we're going to evaluate x2 at 0, which x2 is on the screen up here. That's 1/2 e to the 7t plus 3/2 e to the minus t at t equals 0. And we go ahead and grab that 0 and plug it in for both cases in t. That's going to give me 1/2 e to the 0 plus 3/2 e to the negative 0, which just as before, both e to the 0 and e to the negative 0 are 1, leaving us with 1/2 plus 3/2, also known as 4/2, also known as 2. And so we've checked both of these, both of them on the left, and that's what it means to go ahead and verify all 4 of these properties. That's those 4 cases we just checked below. It's really not too bad of a section, as long as we're content receiving maybe an ODE in this form, and then being able to effectively translate that ODE into a matrix form, which is the way that our solution and the matrix exponential can handle it. So we'll stop there, get some more practice in the next video. I'll see you then. Bye.